Okay, hello everyone. My name is Tomáš and I am AI software engineer at Whalebone. And today I want to share with you how we build a multi-agent system in Go in our company. We are currently using it for our chatbot, which is running on Slack, and it helps us gather some information from our knowledge base or some other providers we are using. We build it via Google's ADK framework. I'm not sure if you are already familiar with it. Maybe is there anyone using the ADK? Okay, good. So I will walk you through the overall architecture and a few patterns we used. So stick with me and we'll go through this. Before we go into details, I will show you the whole system on this slide. Don't try to memorize it. I just want you to have some rough mental picture for the talk. So basically, we are using Slack as an interface for the users, and users are asking questions on the Slack. The whole application, all the agents, everything together is deployed in Kubernetes, and we are just exposing some handlers from events from Slack. So user asks the question, Slack send event to our application, and then we forward it to the agents. You can see in the middle there is orchestrator, and next to it there is a synthesizer agent. Orchestrator is basically the brain of everything. And you can see under the orchestrator on the left, all of everything under orchestrator are tools. And specifically on the left, those tools are functional. This means that these tools are not using any LLM. They are basically some functions in Go that can execute some code, doing some HTTP request, and so on. On the left, you see the knowledge base. We are using Vertex AI for our knowledge base. We are basically indexing our documents from Google Drive, Confluence, and multiple other sources to Vertex AI. And as you can see, you can also connect to Nathan agent or Slack API. On the right, there are different type of tools. Those are agents. And you can see the first one is allow list agent. We are using this agent for determining if any of our or any software we want to use in our company is secure. So this agent has tools as well. The first one is just getting the documentation, how we handle these softwares, and the second one is doing SERP API request for some search about the software. And next, you see the new agent, centralized data access agents. This one is interesting and pretty much new. We are using this for connecting to our databases. As you can see, there are 4 agents, Elastic, ClickHouse, and the first 2 agents are for Postgres. And they are just connected to MCP toolbox servers, which are running in every cluster and region we have. And this is basically converting a human query to SQL and executing this in the databases. And the last one, or on the right, there are just, not sure if it's visible, Atlassian, Asana, HubSpot providers, and this is MCP for those providers. So user can ask questions on those providers. That's basically it. If I strip all that complexity away, the pattern I want to talk about today is just 2 agents and parallel tool call fan out in between. So one agent routes the orchestrator and one agent writes synthesizer. It's simple. So important thing is that this takes only 2 LLM calls per user message, and because orchestrator fires all of the tools in parallel, synthesizer is just writing, collecting the output and writing the single response based on all their outputs. Everything is handled by the free ADK primitives, which makes it possible. The runner, this drives the outer loop and streams the event back to the caller, and the session which is shared for both agents. And last one is instruction provider, which lets us build the system prompt dynamically at invocation time. I will talk all about this very soon. So let's talk about the orchestration. This is the biggest latency win in our system, and it comes down into one flag. In traditional agent loop, the model calls are just like on the top section like this. You have LLM is calling the tool, then it reasons, then call possibly another tool, and then it reasons again. The orchestration pattern we are using is basically planner. The orchestrator will decide based on the user question what tools it needs to call, and it just fires all the tools in parallel, and that's it. No other LLM reasoning after the tools were executed. All the raw outputs from the tools are just passed back to the synthesizer, and then the synthesizer is doing the second LLM reasoning and call. Okay, let's talk about the session state and memory. Session is basically the container of the events. You can imagine it like when you are talking to ChatGPT or something, you have some session, and when you open a new session, you have basically the new session. And we are using this for the Slack threads. Each Slack thread where people are asking the questions is a single session. So state is basically a key value map inside the session. It's how agents can possibly pass data to each other without going through the LLM. And there are some prefixes for the session. Temp is, for example, just temporary state. For state, temp is temporary state. It means that it will live in one invocation. After the user question is finished, this state just is gone. And the last one is memory, is cross-session searchable archive. We currently don't use it today. We don't need that kind of personalization right now, but it's worth knowing it exists. Now let's look inside the session. Every training conversation is a sequence of immutable events, basically an append lock. And each event carries a content, message, function call, tool response, and also can carry some metadata, state changes. One important detail is that the state changes only become visible after the runner commits the event, so that makes the whole thing replayable. Look at the example on the right. The user asks the question about Jira ticket, that's the event 1. The orchestrator calls the Atlassian tool, that's event 2, and the tool comes back with results, which is event 3, and the last one is the synthesizer, which writes the final answer, event 4. Okay, let me show you a real example where state really pays off. So now we are going to talk about state. This is from our data access pipeline. That is the one that answers questions about our internal databases. The first step is to figure out which customers the user is asking for, and importantly, we do this resolution in Go, not in the LLM. We hit our central authentication service, do some fuzzy name matching, check access, permission, which are all deterministic, and then we write the resolved customer list into the session state. The second step reads that list from the state, and using Go routines, we spawn one agent per customer in parallel. Each runs its own agent against the right regional database. The important thing here is that the LLM never sees actual customer IDs, so it just receives them via the state. So the agents are moving the data between each other. And one level deeper, each child agent gets its own customer ID, and this basically means that when we are executing on the right the retail query to the database, this customer ID is put to the SQL query deterministically, so LLM is not putting it there. This is very important to not mix the customer data because, as everyone knows, agents or LLM can make some mistakes. Let's now talk about the contracts between agents and tools. So this one will feel natural to you as a Go developers. We like types, we like knowing what goes in, what comes out. LLMs are the opposite. So if you build a multi-agent pipeline on top of unstructured text, you will spend your time regex parsing model output and hoping it doesn't drift. So ADK gives you two things to bring contracts back. Input schema, which validates what caller passes to an agent before the LLM is even called. And output schema on the right is interesting one. It passes a JSON schema to the model, like Gemini, and the model is constrained at the decoder level to produce a JSON matching that schema. So we are using input schema almost every time and output schema whenever we want some structured output from the agent. Okay, let's talk now about the instruction provider. And basically this means how we are building the system prompts. So this is probably my favorite pattern from the whole project. So our synthesizer agent, which is writing the answer for the user, needs to format this answer differently depending on which tool were used. And if the knowledge base, for example, was queried, we want some citations to it. If the software list tool were called, we want to render some category, structure, everything. And if the commercial desk agent, for example, ran, we want some specific template, summary, quotes, next steps. So basically, you can see on the step one. So orchestrator calls those three tools, and each tool wants some different format from the synthesizer as the output. The naive approach of this is just stuff all of those formatting rules into one big system prompt. We tried that, quality got worse because the model was distracted by the rules that didn't apply, and also latency went up because every call was shipping all those extra tokens. So you basically don't need to tell synthesizer how to format every tool that exists, but only the tools that were actually executed. So the better approach is to make the system prompt a function of what actually happened. ADK supports this through the instruction provider, and instead of static prompt string, you pass a function. The function runs before every LLM, reads the session state, and returns the right prompt for the specific invocation. And here is how we do it. After each tool run, we record its name in session state. Each tool writes its own key. Yeah? And each tool ships with its own formatting snippet embedded in the Markdown file. Before the synthesizer run, the instruction provider just reads the tool output, which were called, and picks the matching snippets and substitute them in the base prompt. So thanks to this, the synthesizer only sees the formatting rules that the tool actually ran. So you pay only for what is used. Okay, now let's talk about another pattern. As I told you before, our orchestrator is a planner, but we have some agents that are running on the first approach, which is tool call reason, and for example, MCP agents are working like that. And there are some issues you can experience with these kind of agents. So we built a free level of protection for this. Okay, so I will start explaining what's the problem actually. Imagine you have MCP call to the, for example, Atlassian MCP, and you are asking the question, and the agent can call multiple MCP calls and trying to find the answer for you. Sometimes it can't find the answer right away, and it is calling the MCP remote server multiple times. It can get stuck, it can take a lot of time, and we have to somehow restrict this. So we have built 3 layers of protection. First one is the soft, second one is the hard, and the last one is just some safety net. The first one is interesting because we have some context deadlines for each agent, so it doesn't run indefinitely. And for example, imagine you have an agent that has restricted to run maximum 10 minutes. And the first approach, the soft, is just telling the agent 2 minutes are left on the deadline, and we are doing it like that. We are appending an urgency instruction to the system prompt, asking the model to wrap up. Yeah, so this works 95% of time. Sometimes the model just ignores us and continues executing the tools. So that's why we need the hard timeout. 50 seconds before the deadline, we are just force terminating, but returning a synthetic LLM response. So the ADK treats it as a final answer. And the last safety net is capping the number of calls to the MCP server for some number of iterations, like 40, for example. That's it. Now let's talk about the resilience. Whenever we call the LLM, we wrap the call in the layer that each handle a different kind of failure, because there are multiple issues or multiple things that can go wrong. Not all of the issues could be related to your code. Sometimes the Gemini has resource exhausted or it's not working for some reason, so you need some resilience strategies. Layer 1 is the transport, HTTP, gRPC connection pooling. When some sockets drops or sort of things, the Go sender library is taking care of it. Layer 2 is backoff. On quota errors, we wait with exponential backoff and jitter, bounded at the retries. Layer 3 is model fallback. If the primary model is out, we route the same request to a different one with a separate quota pool. The agent code doesn't know about this at all. Both models implement the same ADK model interface. It's just Go interface composition. And layer 4 is the LLM itself. If tool throws, we convert the error into structure function response and hand it back. The model can retry with different arguments, pick another tool, or just tell the user something went wrong. Okay, now let's talk about the citations. I'm not sure if anyone tried to do this, how to do citations when using the LLM. But one practical pattern worth mentioning is never let the LLM produce the URLs for your citations. If you ask a model to output a URL, it will confidently produce something that looks plausible but often doesn't exist, or there is some typo or something. So what we do instead is we are letting the model cite the sources using the inline citations. Those are just numbers, like like here. And at search time, we get the chunks with metadata back from the Vertex search, and we build map from each number to the real URL. After the synthesizer writes the answer, we run some regex, replacing the numbers with the actual Slack formatted links. The insight is that the numbers are simple tokens, very hard to hallucinate, and LLM can handle this pretty well. Okay, this is the last slide, I think. Observability. ADK supports via web UI some observability. This is pretty much new. And as you know, debugging an LLM system without traces is painful. When the user tells you the bot gave the wrong answer, you need to know which model called, which tool, which query produces it. So we instrumented everything with OpenTelemetry from the day one. Free primitives matters. You can have some spans. You can have some observability on agent invocation, and I will show you how it looks like on the demo more. Okay, I've just wrap up everything I said, and then we go to demo. So very quick summary. Orchestrator routes, synthesizer writes. This is simple, 2 LLMs, one call per each turn. Then next is ship only the prompt you actually need, assembled from state. So another point is use always input and output schema when you need to. They turn agents into type function. It's really good to use it. And coordination is real bottleneck, not the model. If you have more and more tools, it can get really quickly wrong, so try to design it that the agent can handle it. And also keep the URLs out of the LLM, and the last one is to instrument, use the traces, check it always. Okay, now let's go to see how it looks like. So I need to change. Okay, so let's start with the ADK. So currently I run the web UI from the ADK when you can debug the questions. So let me put there some question I have here. Let's try this with this one. Okay, I will try. Better? Better? I'm not sure how it scales with this UI.
Read the question. Read the question.
Okay, I will read the question. The question was, what I need to do when leaving the office as the last person, and are we allowed to use a Gemini in our company? So basically, I want to show you multi-part questions where are calling multiple tools. So you see right now that the knowledge base tool were called, and you see the question that orchestrator passed as the query. And the second tool was software allow list. Basically, orchestrator found that this is Gemini is the tool that the user is asking, and passed this name to the software allow list agent. Okay, and now there is some answer. That's pretty much it. I will run the second question, and then I will show you what can you also see in the ADK. So the question is, search on Slack in engineering help desk and DevOps help desk channels for log stash issues. So it runs the knowledge base, And as you can see, the query is log stash issues. It sends also, it sends also the Slack channels and the source as the last part. This means that orchestrator parsed the Slack channel names and also the source as a Slack, and all of those informations we need for the actual Vertex search. So we tell the Vertex search, okay, search only on Slack as the source, and search only in these channels, and this is the query. This is useful because we have connected multiple data sources in the Vertex search, and we need to restrict what Vertex search can see at this time. So we are just using the input schema and providing the data via orchestrator to the function tool. Okay, so what else you can see in the ADK? When I click on the event, you see now there are 4 events. The first one was user question, that's the event 1, as I told before. Then the second one was the function call for the orchestrator. And now you can see on the left the query, the Slack channels, and the source. Those are the arguments orchestrator passed to the function. And the third event is function response from the knowledge base, and the last one is the response from the synthesizer, which is basically some string text. Okay, what else you can see in the ADK? I talk about traces, so let's look at it very fast. So this is basically how it looks like. There is some time, how long it took all the invocation. You can see 17 seconds. Then you see the orchestrator was run. It executes the knowledge base, and then you can see the synthesizer, which runs as well. So you see the traces, you see the spans. I think that's it from the ADK, and the last thing I want to show you is how it looks like on Slack. So, yeah, okay. So I will try to put there some message. Yes, let's try with this one. So the question is, look at Jira and provide me details about some task. Okay, so I will run it. Oh, sorry, I have to run the server first. Okay. Okay, it's running. You can see it is streaming the tool calls, and now it is streaming the answer. So I received the answer that I have to authorize with Atlassian. That's because, as I told you, we have multiple providers, and all of those providers are using the OAuth. So we are able to provide our users access to Atlassian, HubSpot, Asana with the scoped responses from what user can actually see. So I'm able to see on our Atlassian only what I can see there. So when I authorize with it, I will just approve it. Okay, authorization successful. I will go back to the Slack, and I will tell the agent, try again. Okay. And now it is querying the Jira. This will take like a few seconds. Okay, it's done. And now it is constructing the answer. Okay, it's done. So now I received back answer from our Atlassian tool. So I see there was some task about centralized data access configuration. Okay, I have one more question here. This is for multiple tool calls. The question is, explain me how retail works and list my in-progress Jira tickets. So when I run this should trigger two tools. Yes, the search knowledge base, which runs really fast. It's like in under 1 second, and the second one is still running. Okay, let it finish in a second. And then I will show you how the citation looks like. And okay. Okay, it's done. So I received 2 answers, how retail works, what was the first part of the question, and those are my in-progress tickets. And now you can see the citations, which basically you can see the sources, Slack, Confluence, Google Drive. We have currently 4 sources, and the Vertex Search found all of these. Yeah, so when I click on this, for example, it will move me back to the Slack thread where the stuff is discussed. Or, for example, this is linked to the Confluence. And these, what you can see here, are basically some suggestions what user can ask as a next questions. This is constructed via Vertex as well. They provide some answer API for these, and this can basically run the user query and analyze all the possible semantic similar questions you can ask. So when I click on this, it should execute the questions for me. Yeah. Okay, and that's basically it from me today. So thank you very much.